Okay, and then here,
Yeah.
Okay, let's go over these problems that were asked on the homework. 7.5. So 7.5 is a pretty tricky one. It says a fly beats its wing at a frequency of 1200 hertz. If the expansion and contraction of the wing muscles of the fly exhibit simple harmonic motion, the angular displacement of each wing of the fly also exhibits simple harmonic motion. The length of the wing muscles varies from 750 micrometers or microns to 600 microns over the course of one beat of its 1 centimeter long wings, and the wingtips move to an arc of 150 degrees. Okay, so first of all, let's go ahead and see if we can get our picture, our head around what's going on. My picture that I get from all that is I have a wing that is 1 centimeter long, and then there's attached to it somewhere is a muscle. So this thing, this muscle goes up and down. All right, and as this muscle goes up and down, the tip of the wing oscillates back and forth, you know. And then this muscle, the amplitude, this muscle contracts. So maybe we'll attach it down here somewhere. This muscle has a length that is maximum distance of 750 microns and minimum 600 microns. Okay, and here's the little rotation thing. Okay, let me just write this down. It says that the wing beats at frequency is 1200 hertz. And 1 centimeter long, and then the angle here actually is much bigger than as I have it drawn. It's 150 degrees. So actually this wing goes all the way down to here and all the way up to like here, 150 degrees. Okay? All right. It says, what is the time period of a single beat of the fly's wings? So that one's pretty easy, right? How do you get period if you know a frequency?
1 over.
So if the frequency, that's how many beats per second it is. 1200 beats per second, so the period would be 1 over that. Which is 1 over 1200 hertz, and you know, whatever that is. So B, what is the maximum velocity of the mobile end of the wing muscle? All right, so we're interested in right up here where the wing muscle is pulling on this wing. And it does simple harmonic motion from 600 microns to 750 microns. So if I were to just kind of graph the tip of this wing muscle, it oscillates back and forth. The center position would be x equals, let's just call the distance of y. Okay, we'll do it y. Let's say the equilibrium position here would be halfway in between those maximum and minimum, right? So 750 up here, 600 down here. So I would do 675 microns is my equilibrium position, and then it goes back and forth between these two extremum with simple harmonic motion. And the question is, what is the maximum velocity of the mobile end of the wing muscle? Well, let's go back to our picture of picturing simple harmonic motion as the x position of a rotating point on a wheel.
Why is that 675 micrometer?
It's half.
Oh, half of it. Okay.
Yeah.
Okay.
look at our rotating circle, and it has a speed v. If we look at it from the side, you know, a point on the edge of this circle oscillates back and forth. It looks like it's oscillating with simple harmonic motion. Clearly, the fastest position would be when it looks right in front of you, right? Because over here it's kind of going away, and over here it's kind of going toward. So, you know, the V is kind of spinning around like that, right? So right in front of you, or the equilibrium position, is where it's going through its maximum position. It would be looking like it was moving with a speed v. So this speed v, this is the equivalent circle problem. It's not actually the speed that it's moving here. It is the speed that it's moving at its maximum speed. So this speed v, I can get, if I look at this r, v is equal to omega r, right? Omega is what in terms of frequency?
2 pi over t.
Yeah.
2 pi over t, yeah, or just 2 pi f, right?
Yes.
2 pi f, and we know what all those are. So r, so if this goes from here to here, this is what the simple harmonic motion looks like. So the r is the same as the amplitude, right?
Yeah.
So this thing here, the 75 micron, is going to be equal to r, the amplitude. So I'm just going to take this, plug everything in here. So V max. And this is the V of a point on the equivalent circle. That's the same thing as the very maximum velocity as it would be going at on the actual simple harmonic motion. So V max would be R, so 0.75 times 10 to the minus 6 meters times 2 pi times 1200 hertz. Yeah, that's fine. And what would that, and you know,
Would it be 10 to the negative 6 or 5?
It's negative
75 times 10 to the minus 6.
75. Okay, I thought if it's 7.5, it's minus 5.
70.5 times.
There you go. Okay. I just.
Yeah. Okay, and that'd be your maximum speed. Does that make sense? So on this one, when you're finding maximum speed, go to the equivalent circle with the same frequency of motion. Look at the speed of a point on the edge of the circle. That'll give you maximum speed for simple harmonic motion.
So for the R value, why are we using the midpoint instead of taking 750 minus 600?
Yeah, that's a good question. For simple harmonic motion, if I were to plot it, like the y position and put this is at y equals y naught, the equilibrium position. It goes from the highest point to the lowest point, like this. And we call this distance from the equilibrium position the amplitude. Notice that if I call this x equals 0 here, this would be x equals r. This would be x equals minus r. So it goes between minus r and r, or twice that amplitude. That makes sense?
Yeah.
Okay, the next part. What was the next part? Okay, the next part is what is the maximum angular velocity of the wing?
Is that what we just found in there or not?
Well, you just found
No.
the
max
Angular.
velocity.
max velocity.
No,
of the
I mean
wing.
like the angular velocity 2 pi times my frequency. Would that give you the max?
Let's see. So the tip of this wing goes back and forth, right, like this. Well, how are we going to get that angular velocity?
Isn't it just 2 pi over
Two pi over.
t? Or 2 pi f?
2 pi f over t. Well, so on this one, we gotta kind of be a little careful. If it moved in a full circle, yeah, no problem. You could do that. But because it's doing simple harmonic motion and not oscillating in a full circle, it becomes a little bit trickier, right? Yeah, let's see if we can kind of get our heads around this. This one, by the way, is a tricky problem. Yeah, pretty good stuff. Okay, we did know what we know the frequency of the wing to be, right? So the wing, I'm going to imagine this is my wing. And then this tip of the wing goes back and forth between its maximum value and its minimum value, executing simple harmonic motion. But it's kind of a weird simple harmonic motion. It's actually on a curve, you see. So it's kind of going, so if I call this its center point, it'll be going back and forth along this curve. Now I know that this 150 degrees corresponds to moving some point over here by 150 microns, right? So some point over here moved 150 micrometers. That's the 750 minus 600 micrometers. This point here moved up and down like that, right? Yeah. So, is there a way that I could maybe figure out? Yeah, I know the maximum speed of this being moved here. Is there a way I could maybe figure out the maximum speed of this being moved, or a maximum, maybe even if I had the angular frequency of this, I guess it would be fine, wouldn't I? And then that would give me, well, okay, let's see what we got. I'm sorry,
I think you were talking about the next.
The wing is a centimeter.
1 centimeter.
And you can find it.
Yes. We are doing maximum angular velocity. The next one's maximum speed.
Yeah.
Okay.
You're confused.
So I didn't mean to confuse you. So what was the maximum speed that we had for that wingtip thing? For the muscle?
The Vmax?
Yeah, the Vmax.
0.565 meters per second.
0.565
565
meters per second. Okay. Are you sure?
That's what I
I got that too.
Okay. Oh, yeah. It's good. All right, I believe it. Okay. So we know that the frequency of this, the angular frequency, is this, right? That's the angular frequency of this going back and forth.
Is that the max angular frequency?
Well, that's the angular frequency of the going back and forth.
Okay.
So that'd be like the equivalent circle problem, right?
Okay.
So that means this thing goes back and forth. These things go back and forth like this with the same frequency, right? So omega is 2 pi times 1200 hertz. Now, how far did it actually move in this time?
One.
2.62 radians?
Yeah.
Okay, so okay, let's convert this 150 degrees to radians. It's always good to do that, if we can. So 150 degrees, how do we convert to radians?
Times pi divided by 180.
360
No,
degrees, okay.
180.
And
Oh,
so,
well,
you got 6.65.
Well, that's the same thing, but I'm saying this is the, you do the right answer.
Okay, something like that, that's what you said?
Yeah, that's what I get.
Okay.
2.62.
So that means that this distance moved here is actually 1 centimeter. Radius times the times the angle will give you the distance, arc length. So r theta is arc length. So this distance moved here on that arc would be 2.65 centimeters. Right?
2.2. I mean 2.62.
6.2. Okay. So the amplitude of motion would be half of that, right? So half of that, so this
75.
distance here would be 1.31, right?
Yeah.
Yeah.
So I'm going to look at the equivalent circle problem and imagine that this point here is like it's like I'm looking at the edge of a wheel, and we're going to treat this more or less as like I'm looking along the motion. So the equivalent circle problem has a radius of 1.31 centimeters and an angular frequency equal to this. Okay. Right? So this thing moving around, what's the maximum speed we would see? This thing would be looking like it's moving around, and if I look at it from the side, here, I see a point on the edge of this circle moving around, executing simple harmonic motion in that direction.
It'd be r omega.
Yep, so V max is r omega. That's the maximum speed at this point. Now, I can also get what the angular speed is if I get, so V max is r, which in this case is 1.31 centimeters, the r of the equivalent circle problem, times omega, which is here. And that's the maximum speed I would see at this point as it goes through its equilibrium point. Omega, the angular speed, I don't want to confuse it with this omega, different, equals V max divided by 1 centimeter. Okay? And so this would be part D and this would be part C.
Yeah. So do they ask it kind of backwards?
Well, maybe they might do it a different way than me, but this is just, I kind of like to get my head around the problem and just work through it. However which way I get it, I get it. So. All right, that was problem 7.5. That's probably the hardest problem, I guess. And what we're really doing is we're translating simple harmonic motion into viewing a circle, an equivalent circle, from the side. And then that's how we get everything. Okay? And then we have to go
You
back.
get the tip of the wings going in a different circle.
Yes. So even though the wing is moving in an arc like this isn't the same circle. This has nothing to do with this circle here.
So the first omega is your maximum angular velocity that you're gonna have, and then the second one is the average.
No, this is my maximum. This is the angular velocity of the equivalent circle.
Yeah.
Yeah. So it would be when you're at the point, when you're moving across in the middle, it's gonna be your maximum angular velocity. Correct?
Not quite. Well, not quite. That's
That point. Yeah.
yeah. If I'm looking at it, then my maximum speed would be r times n omega.
Okay.
Okay. That's about all I can get out of that. And then I have a different r here of the actual arc that this is moving.
So, angular speed is a different equation than angular velocity.
Yeah.
That you divide your time by, if we're gonna get an average, in this case, it's gonna be halfway between Yeah, another way to get any map.
That might work. That sounds like it, right? Do you get the same answer?
I'm not sure about
I
that.
have to think about that for a second. Okay, let's do it a little, let's see if we can do something that's slightly easier. 7.8. Well, actually, let's do 7.4. So 7.4, when a sound wave with a certain intensity is detected by the tympanic membrane, that's your eardrum, I guess. The amplitude of the resultant motion is 1 nanometers. If the frequency of the sound is 600 hertz, what is the maximum speed of the membrane oscillation? So let's say I have an eardrum. Let's look at the cross section of it. I take a little bit of a chunk of this. And this thing, when a sound wave goes down, goes up and down with an amplitude of 1 nanometer. So that's actually pretty tight. 1 nanometer. And it says, if the frequency of the sound is 600 hertz, what's the maximum speed of this thing? So let's go ahead and we'll draw the equivalent circle problem. So this one, we're going to treat this as the amplitude of the oscillation is a radius of this circle. So we take a 1 nanometer radius circle. And it has a frequency, angular frequency of omega, which is 600
Hertz. But that's
times
frequency.
2 pi.
Oh, yeah.
Times 2 pi. Okay. And if I look at it from the side, well, okay, let's look at it from the side this way. So a point on the edge of this would be looking like it's moving up and down like that pendulum. Going at its fastest speed when it's right in front of it. So B max. And that would just be this 1 nanometers times this omega would be the, and that would be this B max is the same as the B of this circle, the edge of the circle. That would be 1 nanometer times 600 hertz times 2 pi. So that's 1 times 10 to the 9, negative 9. And so do this and that you'll get the maximum speed. Okay, 7.8. A small 5-gram fly is buzzing along it and hits a spider web. The spider web catches the fly and proceeds to oscillate with a time period of 0.09 seconds and an initial amplitude of 1.9 centimeters. With what velocity was the fly flying before it hit the web? Okay, this is a good one. These simple harmonic motion ones are all good. I like them. Pretty much.
Wait, I thought
That's
it was
7.8,
which one is
right?
this?
7.8.
7.8.
This one?
Yeah.
Which one
Oh,
was the fly
they mean the
one?
problem we're doing.
Yeah.
Yeah, 7.8.
Okay, that's what it.
Okay, yes. Okay, so I have a fly buzzing along with some speed v. Hits a spider web. I'm going to treat the spider web as a little spring. So it's a spider web. That's what it says, somewhere like motion.
Yeah.
Okay. And then the spider web catches the fly and proceeds to oscillate So back and forth like this, with an amplitude of
1.9 centimeters.
1.9 centimeters. 1.9 centimeters, and a frequency, or a time, and a period of 0.9 seconds. 0.09.
Yeah.
And this is 5 grams. I'm just going to call it now. And so the question is, what's the speed that we have? That's part A. So so we got to kind of think about this for a little bit. This will be an energy one. So when this fly hits the web, which we'll treat as a little spring, starts to move back and forth like that. And if it's simple harmonic motion, we can introduce a spring constant K, right? Assuming that this was conservative, the energy should be the same before it hits the fly or before it hits the web, and then after it hits the web. So initially, the energy was 1/2 mv squared. That's the initial energy.